When you hear more than one musical note at a time, you can perceive the combination as consonant or dissonant. The way you heard that depended on an interplay of culture, physics, and biology, but most likely you heard those first two notes as dissonant. That's what dissonance sounds like. Those two white keys right next to each other on the piano keyboard clash with each other. But after that, the dissonance resolves. When people in Europe first started using harmony 1,000 years ago, they only used consonants. To the modern ear, it sounds peaceful but a little boring. At some point, musicians figured out how to mix in dissonance with the consonants to create a cycle of tension and release. Some things in the arts are just a matter of culture. But the way we perceive sounds as consonant or dissonant depends heavily on biology and physics, and some aspects of our perception are completely cross-cultural. One way in which our brains are hardwired musically is the way we perceive the pitch relationship of a musical octave. An octave is the length of a musical scale. In the Hollywood musical version of The Wizard of Oz, Judy Garland's big song, Somewhere Over the Rainbow, starts with two notes an octave apart. At one point in the Charlie Parker tune Salt Peanuts, the horn players take their instruments away from their mouths and sing, Salt Peanuts, which is also a musical octave. Physically, an octave is a factor of 2 in frequency. The graph on the bottom is a pure sine wave with a frequency of 100 Hz. Here's what it sounds like. The top graph is at the frequency an octave above it, 200 Hz. It does 2 vibrations in the same time it takes the lower frequency wave to vibrate once. Now let's hear them on top of each other. To help you distinguish them, I'll start the low one, then the high one. Once the second wave starts up, the sound you get is the funny-looking wiggle that you get by adding together the 2 sine waves with different frequencies. Here's what it sounds like when I start them at exactly the same time. Your ear hears them as one unit, rather than as 2 separate sounds. An octave is the most consonant combination of notes. In fact, the human ear-brain system is hardwired to perceive notes an octave apart as being almost the same. When a group of men, women, and children sing a song like Happy Birthday in unison, usually they'll all be singing it in different octaves without even realizing it. Perceptually, the spectrum of musical pitch wraps around on itself like a circle or a helix. even though the physical spectrum of frequencies is a line. This is similar to the way that our eye-brain system wraps the visible part of the linear spectrum around to make a color wheel. A similar blending phenomenon happens any time we combine a set of sine waves that are all multiples of a basic frequency. In this example, we combine the first 4 multiples of 100 Hz, which makes a wave with a sort of triangular shape. The basic wave, or fundamental, repeats once every 100th of a second. The wave with double the frequency repeats twice in that time, and the others 3 and 4 times, so that by the time 100th of a second has gone by, they're all back together again and ready to start over. That is, any combination of sine waves with this pattern will be a repeating or periodic wave. The converse, which is more surprising, is a mathematical result called Fourier's Theorem. It says that any periodic wave can be made by combining sine waves like this. As an example, here's a recording of me singing the vowel O with a fundamental frequency of 100 Hz. I think you can see that it's periodic. There's a repeating pattern that looks like a double M. Because it's a periodic wave with a period of 100th of a second, we can think of it as a combination of sine waves with frequencies that are multiples of 100 Hz. Here's the same sound, but with all the frequencies above 100 Hz filtered out. Now let's put the 200 Hz part back in. Now 100, 200, and 300 Hz. Now I'll continue the process by adding in the other sine waves one by one until we get 8 of them. With only the 100 Hz sine wave, it just sounded like a sine wave. It didn't sound like a human voice at all, it sounded like a machine. But by the time we had 8 sine waves put together, to me it sounded indistinguishable from the original recording. Let's hear the whole process again as I add the sine waves in, one by one. Here's what that sound looks like when we display it on a graph of loudness versus frequency. We get an evenly spaced picket fence pattern made of spikes that represent sharply defined frequencies of 100 Hz, 200 Hz, and so on, called the harmonics. This is the key to understanding why our ears hear dissonance and consonance the way they do. Usually, the first 4 or 5 harmonics of a sound are the loudest. If you hear 2 different sets of harmonics at once, the loudest harmonics may or may not clash. If 2 loud harmonics are within about 1% of each other in frequency, they sound like a single sine wave to our ear-brain system. If they're more than about 10% different in frequency, they're not close enough to clash. But if they differ by more than 1% and less than 10%, they cause a clash and the whole thing sounds dissonant. Those were 2 consonant notes. The fundamentals are in the ratio of 3 to 2, so every frequency in the higher note exactly coincided with one of the frequencies in the lower note. Those notes were dissonant. Some of the frequencies clash, so the 2 notes sound dissonant overall. What I've been explaining is a particular scientific model of consonance and dissonance that was developed around 1970. Scientific models aren't absolute truth, but this one worked pretty well. If you heard about some older model in a music theory class, it's probably wrong. If you're interested in more detailed scientific information about this kind of thing, Professor David Huron at Ohio State University has a very nice online outline of the literature, which you can easily find by Googling on his name and his course, Music 829B. Thanks for listening. I hope you learned something.